In a faraway galaxy, a supermassive black hole produced the most potent explosion ever documented, an event so enormous it possessed the power to obliterate whole groupings of stars. What triggered this incomprehensible detonation? Furthermore, what insights does it offer regarding the concealed energies that sculpt our cosmos? If you find investigating celestial enigmas captivating, we invite you to please like, subscribe, and distribute this content. And be sure to tell us in the comments what your hypothesis is regarding the energy source for something this powerful. We appreciate your viewership. Let us now commence. Located within the southern constellation, known as Phoenix, exists an object of truly remarkable proportions. It is an assemblage of galaxies, held in cohesion by the forces of gravity and the passage of eons. The Phoenix cluster extends over distances spanning millions of light years. Its complete mass totals quadrillions of times the mass of our own Sun. To the unaided human eye, this structure would be completely unseen. It is too remote and too dim to make any impression on the nocturnal sky. However, to the sophisticated tools of contemporary astronomy, it emits a gentle radiance in X-rays, identifying itself as an immense repository of both material and power. Every galaxy inside it glides through the cluster's immense gravitational influence as though hanging in suspended animation, their combined motions creating an expansive and soundless dance, a choreography that has persisted for many billions of years. Within this colossal setting, galaxies do not exist as secluded islands. Rather, they are active participants in an unbroken interchange of gas, fine particles, and the enigmatic dark matter. The cluster's assembly commenced in the early epochs of cosmic time, back when the force of gravity pulled together lesser collections of galaxies, along with the dark halos enveloping them. Through the ages, these structures coalesced into one solitary entity, possessing tremendous density. This amalgamation liberated vast energy, which raised the temperature of the intergalactic gas to levels reaching tens of millions of degrees. This intense heat forced it to radiate the very X-rays that initially revealed its existence. Data gathered by observatories like the Chandra and XMM Newton missions confirm this gas permeates almost the entirety of the volume separating the galaxies. The Phoenix cluster stands out as one of the most brilliant X-ray emitters in the entire known cosmos. It is a lighthouse of superheated plasma shining from a separation of almost 6 billion light-years. Its photons originating from it started their epic voyage when planet Earth was in its infancy, traversing vast cosmic emptiness and passing through obstructing structures prior to arriving at our contemporary detectors. The information they carry unveils a complex system where every single scale, from the most minuscule star up to the whole cluster's halo, takes part in an equilibrium between cooling processes and heating processes, gravitational collapse, and outward expansion. Contained within the Phoenix cluster, many hundreds of distinct galaxies revolve around a mutual center of mass. A portion of these are ancient ellipticals, appearing faded and indistinct, their stellar populations formed long ago. Still others are spirals, identifiable by their delicate arms pulled taut by powerful gravitational tides. Conduits of intergalactic matter link them. These are tendrils of gas extended by gravitational interactions that themselves require hundreds of millions of years to complete. These galaxies are certainly not stationary. They travel through a shared sea of superheated plasma, which is identified as the intracluster medium. This medium is so incredibly tenuous that its density measures far less than any vacuum we can create on Earth. Despite this, its collective mass actually exceeds the mass of all the stars in the cluster put together. Every galaxy that traverses this medium encounters a form of friction from this gas. a drag force known as ram pressure. This force is strong enough to peel away its external layers, leaving in its wake a long trail of gas that is cooling. Over the span of cosmic history, these wakes add to the cluster's slow, progressive enrichment with heavier chemical elements that were synthesized inside preceding generations of stars. The cluster's profound gravitational potential, which is overwhelmingly dictated by invisible dark matter, governs the movement of every single constituent inside it. Maps created using X-rays depict a generally spherical pattern of radiation, which is most intense near the core, the location where the gas is most concentrated. In visible light, the perspective shifts. A dense congregation of galaxies is seen clustered more tightly toward the center, creating the structure that astronomers refer to as the brightest cluster galaxy. This specific central area commands special focus because it signifies the precise location where the cluster's enormous gravitational well reaches its absolute greatest depth. In this location, gas cooling from the external halo starts its gradual migration inward. This cooling effect is unhurried but persistent, a mechanism that has been ongoing for billions of years and one that is capable, given the appropriate circumstances, of triggering intense episodes of stellar creation. However, radiative cooling by itself is insufficient to account for what is actually seen. The intergalactic gas ought to have condensed eons ago, forming new stars at paces much greater than what has been recorded. Some force must be re-injecting energy back into the system, neutralizing the dissipation of heat and preventing the entire cluster from succumbing to collapse under its own immense gravity. This delicate interaction between cooling mechanisms and heating mechanisms is what defines the existence of galaxy clusters. Furthermore, it is precisely inside the Phoenix cluster that this equilibrium attains one of its most spectacular and intense manifestations. The cluster's sheer scale and brightness render it a perfect natural laboratory for comprehending these rivalrous physical processes. Its complete span is calculated in millions of light-years. Nevertheless, the physical characteristics inside it are astonishingly consistent. It is a plasma primarily composed of hydrogen and helium. Its temperature hovers around tens of millions of degrees, and its internal pressure diminishes in a gradual, smooth manner with increasing distance from the core. Analyses using gravitational lensing uncover the existence of dark matter in an amount approximately 5 times greater than the quantity of ordinary matter. The galaxies we see are merely the observable portion of a vastly bigger and more intricate superstructure. As researchers chart the cluster across many wavelengths, from radio waves to visible light to X-rays, they reveal complexities within complexities: shock waves, tendrils, vast voids, and powerful jets. These various features constitute proof of previous energetic activity originating from the central galaxy, a location where a supermassive black hole is injecting vast power into the medium that envelops it. However, when viewed at the grand scale of the entire cluster, these interruptions register only as mild fluctuations within an otherwise homogeneous radiance. The external zones of the Phoenix cluster persist in a mostly unperturbed state, maintaining characteristics analogous to those found in different, similarly massive clusters. In those areas, the gas concentration is reduced and the temperature is marginally elevated, which signals a slower rate of cooling. As one travels inward, the gradient becomes much sharper, and the energy losses from radiation grow more significant. This is the precise area where the cluster's most fascinating mechanisms are revealed. The inward migration of gas, the radiative cooling of the plasma, and the transmission of energy originating from the core collectively establish the dynamic equilibrium that maintains the system's stability. The cluster's gravitational binding energy is so profound that even an eruption of incomprehensible force from its central black hole is only capable of affecting a restricted fraction of its total volume. Nonetheless, that influence is absolutely critical. Without intermittent reheating originating from the core, the surrounding gas would undergo catastrophic cooling, igniting an episode of star creation far in excess of what is actually documented. The Phoenix Cluster, therefore, exists as both an enormous assemblage of galaxies and a completely interlinked ecosystem, sustained by the constant trafficking of energy between its central nucleus and its outer limits. Observed from a great distance, the cluster would seem tranquil, its constituent galaxies gliding languidly inside the radiant fog of the integral cluster medium. But concealed beneath that apparent serenity is a long history of violent collisions, massive mergers, and complex feedback loops that stretch across cosmic ages. Every single photon captured from its X-ray emission transports data concerning the temperature, the density, and the pressure at varying depths. This allows astronomers to meticulously reconstruct the precise physical condition of the gas. The light from the Phoenix Cluster functions as both a historical document and a profound admonition, a document detailing the energy liberated and absorbed over countless eons, and an admonition of just how fragile this equilibrium continues to be. Near the cluster's external boundary, gravity's influence diminishes, and the gas starts to merge into the intergalactic medium that populates the larger cosmic web. Here, the boundary between the cluster and the void is not sharp, but rather a slow tapering off, defined not by distinct perimeters, but by fading light. These outer layers hold remnants of the cluster's assembly, its past, material that is still migrating inward under gravity's pull, transporting angular momentum and trace elements from long-dead supernova. From this immense frontier, one can gaze inward toward the core and discern a clear hierarchy of organization. The diffuse external regions yielding to more concentrated gas, and then to the brilliant inner zones where Phoenix A is situated. It is inside that central galaxy that the cluster's most powerful events transpire, and where the precarious balance between cooling and heating arrives at its absolute tipping point. Yet, for the moment, from the vantage point of the outer reaches, the Phoenix Cluster presents as a singular, cohesive entity. Massive, silent, and glowing, a cosmic metropolis of galaxies suspended within an ocean of hot gas. Its core is hidden, but it is far from dormant. Stretched between the galaxies of the Phoenix Cluster is a boundless ocean of plasma, so incredibly diffuse that a single cubic meter holds just a handful of atoms. Yet, when considered across the immensity of the cluster, this gas possesses more mass than all the stars combined. It constitutes what scientific observers term the intra-cluster medium. This is a continuous shroud of ionized hydrogen and helium, infused with trace amounts of heavier elements bequeathed by ancient supernova explosions. Warmed to tens of millions of degrees Celsius, this gas radiates a subtle X-ray luminescence that permeates the space between galaxies, akin to a shroud of invisible light. This radiation reveals both its internal temperature and its density, enabling scientists to chart the pressure of this medium as it stretches outward for millions upon millions of light years. Its very presence demonstrates that galaxy clusters are not simple collections of galaxies, but are instead fully integrated systems, held in check by dark matter and given stability by the immense weight of this superheated gas. When observed in the X-ray spectrum, the Phoenix Cluster looks like a translucent orb, featuring a more brilliant nucleus where the density and pressure attain their maximum values. The gas is not motionless. Rather, it is in a state of slow motion, cooling in increments as it broadcasts energy into space. If there were no external heating source, This cooling would compel it to condense towards the cluster's core, developing dense filaments that might, in time, provide the fuel for new generations of stars. And yet, the temperature profile remains astonishingly stable, which suggests that some process is perpetually restoring energy to the gas. This invisible mechanism functions on scales of hundreds of thousands of light-years and across timeframes of hundreds of millions of years. Within the Phoenix cluster, the equilibrium between cooling and heating is more precarious than in nearly any other system ever discovered. And it is this equilibrium that dictates its current visual state. The intracluster medium functions as a massive reservoir of potential energy. It reacts to gravitational compression from the cluster's dark matter halo, which applies the primary influence on its overall structure. The gas follows this gravitational terrain, accumulating near the center where the potential well is at its most profound. As it does this, it grows denser and radiates more brightly in X-rays. Detailed observations from the Chandra X-ray Observatory have detected subtle ripples and faint hollows in this emission. These are the signatures of an interaction between the hot gas and the energetic activity of the central galaxy. These indentations are proof that the medium is simultaneously massive and reactive, a dynamic, living chronicle of energy transfer. Every shockwave, ripple, or hollow space logs a previous event in which a jet or an eruption of radiation upset the equilibrium, only for gravity to gradually re-establish it over vast stretches of time. The complete mass of the intracluster medium in Phoenix is staggering, believed to surpass that of all the cluster's galaxies by a factor of several times. This signifies that the majority of the visible matter is not confined within stars, but is instead floating freely in this tenuous plasma. This medium serves as the cluster's connective tissue, sending pressure waves and mechanical force between galaxies that are separated by millions of light-years. Its temperature, maintained near tens of millions of degrees, guarantees that atoms stay stripped of their electrons, creating a plasma where charged particles can travel without restriction. Magnetic fields weave through this plasma, directing the trajectories of particles and assisting in the confinement of the gas within the gravitational well. These fields are minuscule by Earth's standards, yet they are highly consequential over cosmic distances. They affect how energy from the central black hole permeates through the cluster, steering relativistic particles along filamentary paths that can endure for hundreds of millions of years. The gas's radiative cooling time, meaning how long it would require to dissipate its heat if left undisturbed, is shorter near the cluster's nucleus than in its peripheral regions. In the Phoenix cluster, this cooling duration drops below 1 billion years in the inner zones. This implies that without the feedback from the central black hole, the gas would have cooled down and condensed many eons ago. The fact that it continues to glow brightly in X-rays indicates that the process of energy injection has matched, or very nearly matched, the rate of cooling, thus preserving a delicate balance. At these extreme temperatures, the gas emits light chiefly through bremsstrahlung, or breaking radiation. This is a process that happens when electrons are deflected by protons, shedding energy in the form of X-rays. The intensity of this emission discloses both the density and temperature gradients across the cluster. By comparing these gradients against gravitational lensing data, astronomers are able to deduce the total distribution of mass, which includes the predominant dark matter component. The findings confirm that dark matter outweighs normal matter by a ratio of roughly 5:1, dictating the architecture of the entire system. Without this unseen scaffolding, the intracle cluster gas would not be able to remain gravitationally bound. The pressure of the hot plasma is adequate to fend off gravitational collapse, but only just barely. The medium is perpetually in motion. Its particles are colliding, scattering, and slowly radiating away their energy. This loss of heat initiates an inward drift that must be balanced by some type of heating mechanism to avert a runaway cooling scenario. That source of heat is concealed within the central galaxy, where an active nucleus, fueled by a supermassive black hole, sporadically unlepts enormous quantities of energy. The effect of those outbursts travels outward through the intracluster medium, warming it and agitating it, much like a spoon stirring a vast, invisible ocean. The resulting patterns, shock fronts, ripples, and buoyant cavities, all attest to the tight coupling between the central engine and the gas surrounding it. And yet, despite this activity, the medium stays extraordinarily uniform when observed on very large scales. It functions as a sort of thermal buffer, allocating heat and absorbing disturbances across the cluster's immense volume. This smoothness is what permits the Phoenix cluster to retain its spherical shape, even after billions of years of intermittent eruptions from its core. The particles that constitute the medium have lifespans far exceeding those of the stars within the galaxies they envelop. A solitary proton in this gas might meander through the cluster for tens of billions of years without ever escaping, tracing a trajectory dictated by gravity and magnetic fields. These particles collectively form a kind of chronicle of the cluster's past, holding on to the temperature and composition that mirror countless generations of stellar evolution. The heavier elements present, oxygen, iron, silicon, originate from supernova explosions inside the galaxies. Their ejected material is transported outward by galactic winds and blended into the surrounding plasma. Consequently, the intracluster medium is simultaneously the graveyard of previous stars and the womb for potential new ones, depending entirely on whether conditions are more favorable for cooling or for heating. In Phoenix, that rivalry reaches a truly extraordinary intensity. The central areas cool so quickly that gas condenses into filaments and clouds, some of which are visible in optical and ultraviolet light. Concurrently, energy from the black hole's jets inflates cavities that reheat the adjacent plasma, diminishing the flow of cold material inward. The outcome is a continuous cycle that has endured for millions of years, supporting the cluster in a near steady state. To an observer viewing from a remote vantage point, the intracluster medium of Phoenix would look placid, its diffuse luminescence concealing the intricate physics taking place. But beneath that apparent calm, pressure waves are rippling through the plasma, traveling at thousands of kilometers per second. Music. Each individual wave transports information about the last significant eruption from the cluster's nucleus. As these waves propagate outward, they progressively lose their energy, blending into the generalized turbulence of the gas. Over time, the medium absorbs these agitations and reverts to equilibrium, its colossal mass serving as a stabilizing influence. This equilibrium is not static, but rather dynamic, preserved through the unending exchange of energy between the central galaxy and the environment that surrounds it. The Phoenix cluster's intracluster medium, therefore, embodies a microcosm of cosmic balance, a system where the most tenuous particles and the most massive black hole are linked together in a singular process that spans the observable universe. As the superheated plasma of the Phoenix cluster broadcasts its energy into space, it undergoes cooling with exceptional slowness, a process that plays out over hundreds of millions of years. Yet, when measured on cosmic timescales, even such a gradual cooling process becomes highly significant. In the inner zones of the cluster, where the densities are greater and the gas radiates most intensely in X-rays, this loss of heat leads to a drop in pressure. Gravity then pulls the cooler gas inward, generating what astronomers refer to as a cooling flow. The idea is straightforward in principle. As the gas cools, it loses its buoyancy and gradually sinks toward the center of the cluster, where it has the potential to condense into clouds that are dense enough to form entirely new stars. In the majority of galaxy clusters, this inflow of gas is relatively moderate, kept in check by energetic bursts from the central black hole that reheat the gas. In the Phoenix cluster, conversely, the cooling seems to be exceptionally intense. Observations suggest that hundreds of solar masses of gas might be condensing every single year, a rate that dramatically surpasses that seen in more typical clusters. This rapid inflow provides sustenance for both star formation and the central black hole, binding the destiny of the whole system into a single, comprehensive feedback loop. The concept of a cooling flow first appeared decades ago, when astronomers initially mapped the X-ray emissions from clusters and deduced that the central gas must be cooling much more rapidly than the outer halo. If no force opposed this mechanism, massive quantities of material would aggregate near the center, resulting in a continuous cycle of condensation and stellar birth. However, when astronomers searched for this expected cold gas and the resulting new stars, they discovered far less than their models predicted. The absent material strongly suggested that some concealed source of heating had to be intervening. In Phoenix, this persistent puzzle assumes an entirely new magnitude. The cluster's radiative energy losses are colossal, among the highest ever recorded, and yet the gas still remains partially hot. This suggests that the heating and cooling processes are almost, but not flawlessly, in balance. This near-equilibrium state fosters conditions of rare complexity, where both processes can be witnessed occurring simultaneously. The inward migration of gas is not a uniform current. Rather, it manifests as a complex pattern of filaments and knots that stretch for tens of thousands of light-years out from the central galaxy. These filaments are demonstrably cooler than their immediate surroundings and are frequently traced by emissions from molecular hydrogen, carbon monoxide, and other elements that can only form at much lower temperatures. They seem to be connecting the outer intracal cluster medium with the nucleus, serving as channels through which material gradually descends towards the galaxy, located at the center. In optical and ultraviolet light, these filaments possess a faint shimmer, which is evidence of gas cooling through progressive stages as it nears the conditions required for star formation. The mechanism is unhurried, dictated by the complex interplay of gravity, radiative energy loss, and magnetic tension. Each individual filament can remain intact for millions of years, suspended within the hot plasma and steered by magnetic fields that stop it from dissipating too rapidly. The balance of forces within these structures is extremely delicate. Without magnetic support, the filaments would rapidly fragment under the intense pressure of the surrounding medium. Without the surrounding heat, they would cool and collapse entirely. The Phoenix cluster showcases this equilibrium on a scale that is visible across hundreds of thousands of light-years, positioning it as a natural laboratory for investigating how cooling flows function in the most extreme environments. This cooling flow provides direct sustenance to the brightest cluster galaxy, known as Phoenix A. At its core, the gas achieves sufficient density to create stars at a rate that is unmatched by any other known cluster galaxy. Current estimates propose that new stars are forming at a pace of several hundred solar masses annually, a velocity that resembles galaxies from the early universe, rather than those found in mature clusters today. This intense starburst activity converts the inner region into a brilliant network of young stellar populations that are encircled by much older stars. The combination of hot plasma, cooling filaments, and newly born stars generates a spectrum that stretches from X-rays all the way to infrared, permitting astronomers to trace the complete sequence of physical processes within a singular system. However, this apparent abundance conceals a more profound query. If the cooling flow persists without being checked, it should, in time, use up all the available gas and fundamentally alter the cluster's equilibrium. Observations demonstrate, however, that the process seems to be self-regulating. The more gas that cools and migrates inward, the more sustenance it provides to the central black hole. The black hole, in response, unleashes energy that reheats the gas, which in turn slows down any further cooling. This feedback loop guarantees that the cluster stays near a state of equilibrium, never completely collapsing into a massive burst of star formation, nor ever remaining entirely dormant. In Phoenix, this cycle functions at an intensity rarely witnessed. The cooling flow is potent enough to propel vigorous star formation, but it is not so strong that it overwhelms the heating supplied by the black hole's powerful outbursts. The outcome is a dynamic equilibrium, preserved by processes that traverse scales from the subatomic to the intergalactic. On human timescales, the system would look static, its light appearing completely unchanging. Yet every single photon carries unmistakable evidence of this concealed motion. X-ray spectra disclose gas at numerous temperatures, ranging from tens of millions of degrees down to just a few million, which confirms that cooling is happening continuously rather than in isolated bursts. Optical observations pick up emission lines from the cooler gas and young stars, while infrared measurements capture dust that has been warmed by the nearby radiation. Taken together, this data confirms that the cooling flow of Phoenix is not some ancient relic, but is instead an active and ongoing phenomenon. The physics of this particular flow is critically dependent on the interaction between the hot and cold phases of the gas. As the plasma cools, minor instabilities can trigger parts of it to condense more rapidly than other parts, creating clouds that decouple from the surrounding medium. These clouds then fall inward under gravity, occasionally merging with one another, and sometimes evaporating back into the hot gas if they encounter shock waves or significant turbulence. The rate of this condensation dictates how much material eventually arrives at the core and fuels the creation of stars. In Phoenix, the evidence points to condensation being unusually efficient, potentially because the heating from the central black hole is not distributed evenly, permitting certain regions to cool more quickly. This patchwork pattern of heating and cooling is what generates the intricate structures observed in high-resolution data. Each cavity or filament signifies a snapshot in time of the balance between these opposing forces. Over millions of years, this pattern reorganizes as new outbursts from the black hole inject fresh energy and alter the local conditions. Despite these fluctuations, the overall structure of the cooling flow remains, providing evidence that this process has endured for a large portion of the cluster's history. The term flow can be somewhat deceptive, as the motions involved are slow and frequently turbulent, rather than being unidirectional. Gas is swirling, eddying, and circulating within the gravitational potential, shedding heat as it moves. This slow dance of matter constitutes the hidden rhythm of the cluster. It connects the distant outer halo to the absolute innermost regions, guaranteeing that no single part of the system is truly isolated. The Phoenix cluster's cooling flow, therefore, acts as both a source of renewal and a regulator of balance. It restocks the core with fresh material to sustain star formation, and at the same time, it triggers the feedback mechanism that prevents a total collapse. It is the silent mechanism through which gravity, radiation, and magnetism sustain their dialogue across vast cosmic distances. In its measured, steady pace lies the cluster's continuity, a process older than the galaxies themselves, shaping and preserving one of the most luminous structures ever witnessed. At the very center of the Phoenix cluster is its brightest cluster galaxy, which is known as Phoenix A. This is a colossal elliptical structure that holds sway over the gravitational core. This galaxy radiates with the collective light of hundreds of billions of stars. Yet, its incredible brilliance is not merely the product of ancient stellar populations. Embedded deep within its halo are active regions of vigorous star formation, which is a significant rarity among central cluster galaxies. Most galaxies of this type acquire their mass early, their fuel for making stars having been depleted long ago. But Phoenix A stands in defiance of this trend. Its core radiates across numerous wavelengths, revealing complex layers of gas, dust, and young stars coexisting with an active nucleus that propels powerful jets of energetic particles outward. The galaxy's appearance in optical light is deceptively uniform. Its rounded contours imply a sense of calm and stability. Yet, deeper imaging reveals an elaborate web of filaments and knots that stretch for tens of thousands of light-years from its center. These filaments, which are composed of cooling gas being drawn inward from the cluster's hot medium, designate the pathways through which both energy and matter are flowing between the galaxy and the cluster. The stellar content of Phoenix A narrates a story of stark contrast. Encircling its core is a vast population of old stars that were formed billions of years in the past. Their light is yellowish and diffuse. Superimposed upon this ancient backdrop are brilliant blue patches, indicating locations where young, massive stars have only recently ignited. These regions shine intensely in ultraviolet light, providing evidence that the galaxy is continuing to transform gas into stars at a velocity more commonly associated with galaxies in the early universe. Spectroscopic observations suggest that the rate of star formation might be reaching hundreds of solar masses per year. Such activity inside a central cluster galaxy is truly exceptional, signaling that the cooling flow from the surrounding intracal cluster medium has successfully reached the core and has delivered fresh material for stellar birth. The gas that fuels this intense activity likely originates far beyond the galaxy's visible perimeter, pulled inward by gravity as it cools and loses pressure. As it gets closer to the dense environment of the core, the gas fragments into the filaments and clouds, many of which are aligned along the pathways of older outflows from the central black hole. The interaction of this inflow and outflow sculpts the galaxy's inner architecture, generating cavities, arcs, and filaments that trace the energy cycles currently at work. The central zones of Phoenix A are enveloped in a subtle haze of ionized gas that emits powerfully in hydrogen lines, especially in the optical wavelengths. This emission delineates the inner boundaries of the cooling flow, marking the transition point where hot plasma changes into cooler, denser material. Observations conducted in infrared light disclose dust grains intermingled with this gas, which are absorbing ultraviolet radiation and re-emitting it as a faint thermal glow. These grains are the remnants of earlier generations of stars, recycled through the galaxy's unending exchange with its environment. The combination of this dust and ionized gas yields a complex spectral signature that varies with distance from the center, reflecting the fluctuations in temperature and density within the cooling flow. In the radio wavelengths, the galaxy shows an entirely different personality. Twin lobes of emission extend outward from the nucleus, created by jets launched from the central black hole. These jets carve channels directly through the surrounding plasma, inflating huge bubbles of relativistic particles that ascend buoyantly through the integral cluster medium. The cavities they leave behind correspond perfectly to the depressions seen in X-ray maps, demonstrating that the very same activity which powers the jets is also sculpting the distribution of gas around the galaxy. Each cavity signifies an episode of feedback, a specific moment when the black hole unleashed sufficient energy to displace millions of solar masses of gas. The sheer scale of these structures highlights the extraordinary power contained within the nucleus. Yet, despite these violent-seeming processes, the overall appearance of Phoenix A remains orderly, as if the galaxy perpetually re-establishes its equilibrium after every single outburst. The balance between star formation and black hole feedback is what defines its present condition. If the energy liberated by the black hole were significantly stronger, it would heat the surrounding gas so completely that cooling would stop, thereby halting star formation entirely. If it were significantly weaker, the cooling flow would take over, and the galaxy would experience a runaway burst of star creation. In Phoenix A, the two processes are exquisitely tuned, maintaining a coexistence that sustains the entire cluster's structure. The galaxy thus serves as a living demonstration of feedback in action, illustrating how cosmic systems regulate themselves through cycles of heating and cooling that unfold over many millions of years. The light, originating from Phoenix A, transports this balance across space and time. In visible wavelengths, it registers as a diffuse glow centered within a faint halo of stars. In the ultraviolet spectrum, it reveals the intensity of its young stellar populations. In X-rays, it radiates with the intense heat of the integral cluster gas. In radio, it flares with the signatures of powerful jets and lobes that extend far beyond the galaxy itself. Combined, these different wavelengths compose a detailed portrait of a galaxy that is simultaneously ancient and active, tranquil-looking yet highly dynamic. The cluster surrounding it amplifies this duality. The gravitational pressure exerted by the cluster confines the gas that is ejected by the galaxy, stopping it from escaping the system entirely. Instead, this material circulates, rising up, cooling down, and falling back again in a continuous loop. This circulation ensures that the energy injected by the black hole eventually returns to the galaxy in a different form, thereby maintaining the thermal balance of the whole system. In numerous respects, Phoenix A acts less like a solitary galaxy and more like the visible nucleus of an enormous, self-sustaining ecosystem. Within its inner few thousand light-years, the effects of gravity, radiation, and magnetism all converge. The black hole provides the anchor for the system, while the surrounding stars and gas react to its influence. The cooling flow transports fuel inward, while the jets and radiation push energy outward. The outcome is a stable oscillation, a slow heartbeat that dictates the evolution of both the galaxy and the cluster that envelops it. The timescales involved here are immense. A single cycle of heating and cooling can persist for tens of millions of years. Yet, to an observer who is measuring the faint fluctuations in brightness across these wavelengths, the signatures of these cycles stay visible, etched into the very structure of the gas and the physical distribution of the stars. Phoenix A's unique activity has elevated it to an essential subject of study for comprehending how galaxies and clusters co-evolve. It bridges the gap in scale between small star-forming galaxies and the colossal systems powered by supermassive black holes. Its luminous core demonstrates that even in environments dominated by hot plasma, cold gas and star formation are able to persist when the feedback mechanism is precisely balanced. It also underscores the role of the intracluster medium as both a source and a recipient of energy. Every photon emitted from Phoenix's center tells a part of that story, from the ultraviolet light of young stars to the X-rays from shocked gas, and the radio waves from relativistic electrons spiraling along magnetic field lines. Each signal travels for billions of years before it reaches Earth, a silent chronicle of the processes that sculpt the largest structures in the cosmos. As the brightest cluster galaxy, Phoenix A signifies the pivot point between the cluster's expansive outer halo and its active, energy-rich core. It is right here, within this luminous central galaxy, that the grand mechanisms of feedback, cooling, and star formation all converge, setting the stage for the even more profound forces concealed at its nucleus, the black hole, whose power simultaneously sustains and restrains the cluster around it. Deep within the luminous center of Phoenix A, the cooling gas is condensing into vast clouds, where new stars are igniting at an astonishing rate. The core of this galaxy glows intensely with ultraviolet light from thousands of massive young stars, whose lifespans will be measured only in millions of years, a fleeting moment by cosmic standards. In the majority of cluster environments, this level of star formation is considered impossible because the surrounding gas is simply too hot to cool down quickly enough. Yet here in Phoenix, the conditions are highly unusual. The inward flow of cooler plasma from the intracluster medium perpetually delivers fresh fuel, while the feedback from the central black hole modulates rather than completely suppresses the formation of stars. The result is a delicate balance that permits a starburst to flourish in the very heart of a system that is dominated by superheated gas. Observations across multiple wavelengths reveal this ongoing process. In ultraviolet and optical light, astronomers detect bright knots of emission, which correspond to clusters of young stars. Infrared observations reveal dust that has been heated by starlight, glowing softly through the haze of the galaxy's interior. In radio wavelengths, faint signals trace molecular gas, the essential raw material for further stellar birth. Taken together, these findings demonstrate that Phoenix A contains one of the most active star-forming regions ever witnessed in a cluster's central galaxy. The rate of star formation, reaching hundreds of solar masses per year, rivals that of galaxies seen when the universe was only a few billion years old. This classifies Phoenix A as an anomaly, a late-time system that is exhibiting behaviors once believed to be confined only to the distant past. Within these star-forming regions, massive clouds of hydrogen collapse under their own gravity, their densities progressively increasing until nuclear fusion ignites. This process liberates intense radiation that pushes outward, sculpting the surrounding gas into intricate filaments and shells. As clusters of stars form in close proximity to one another, their combined stellar winds carve out cavities in the medium, shaping complex structures that intertwine with the larger-scale filaments being drawn in by the cooling flow. The interplay between these processes fosters a layered environment where young stars illuminate the remnants of the very gas that produced them. Each new generation of stars enriches this environment with heavier elements, seeding the cluster with the materials necessary for planets and, potentially, life elsewhere in the cosmos. Though in this location, the conditions remain far too extreme for such outcomes. The presence of this starburst poses significant questions about how it started and how it manages to persist. In most clusters, feedback from the central black hole actively prevents such intense cooling. But in Phoenix A, the balance appears to be temporarily offset, permitting cooling to proceed at a faster rate than heating for a duration of millions of years. This imbalance might have been initiated by a previous outburst that expanded the surrounding gas, which was then followed by a gradual reduction in the black hole's activity. As the pressure from the jets subsided, cooling resumed, which led to a surge of condensation and the subsequent star formation. Eventually, the renewed inflow of material toward the black hole will inevitably reignite the feedback mechanism and restore the equilibrium. Thus, even this tempest of creation is merely part of a much larger cycle, one that oscillates between phases of quiet dormancy and energetic outburst. The newborn stars of Phoenix A form chiefly in clusters that are scattered throughout the central tens of thousands of light years. Some of these clusters are compact and extremely massive, containing millions of stars, while others are more diffuse and destined to be short-lived. Their combined luminosity dominates the galaxy's ultraviolet output. Surrounding them are clouds of molecular gas, detected through carbon monoxide emissions, which provide clear evidence of the coldest phase of the interstellar medium existing within this cluster environment. The coexistence of such cold gas with the surrounding plasma, which is at tens of millions of degrees, is truly remarkable. It is likely that magnetic fields and pressure gradients effectively insulate these cold clouds, stopping them from evaporating. These protective mechanisms permit the clouds to endure long enough for stars to form before they are ultimately destroyed by radiation and stellar winds. Over time, the energy from these young stars, released through supernova explosions and powerful stellar winds, will return heat to the surrounding gas, partially counteracting the very cooling that fueled their birth. This feedback loop within the galaxy mirrors the larger feedback loop between the galaxy and the cluster, reinforcing the system's self-regulating nature. The light from these particular stars offers astronomers a unique window into the early universe. Galaxies observed billions of light-years away, whose light departed when the cosmos was young, show similar spectra and luminosities to Phoenix A. Studying this cluster, therefore, provides a method to examine ancient processes that are still active in the modern universe. The same physics that governed early galaxy formation continues to operate here, sustained by the unique conditions of the cooling flow and the massive gravitational potential of the cluster. The starburst does not unfold uniformly. Certain regions display intense formation activity, while other regions remain quiescent. This unevenness is a reflection of local variations in density, magnetic structure, and the pressure from radiation. In some locations, the jets from the central black hole might have compressed the gas, triggering a collapse. In other areas, they may have cleared out cavities, temporarily halting star formation. The combination creates a patchwork of light and shadow across the inner galaxy, with each distinct region marking a different stage in the life cycle of gas and stars. Over millions of years, these regions evolve, eventually merging into the diffuse background of the older stellar population. As the most massive new stars deplete their fuel, they explode as supernovae, injecting heavy elements into the surrounding medium. These explosions also drive turbulence, mixing the hot and cold gas and creating the seeds for future star formation once the system eventually cools again. The process, therefore, feeds itself, with each generation of stars shaping the next one. The remarkable luminosity of Phoenix originates not just from its starlight, but also from the interaction between this radiation and the surrounding dust. Dust grains absorb the high-energy photons, and then re-radiate that energy at longer wavelengths, producing a steady infrared glow. Measurements from space telescopes indicate that this dust carries the distinct signature of ongoing star formation, with temperatures that are consistent with heating by young, massive stars rather than by older stellar populations. The presence of this dust also influences how the galaxy evolves by shielding the molecular gas from intense radiation, which allows the cooling to proceed more efficiently. Without such shielding, much of the gas would remain ionized and be unable to condense. The combined effect of stars, dust, and gas fosters an environment that is both luminous and dynamic, sustained by the inflow of material from the cluster's vast reservoir and tempered by the energy released by the black hole's feedback. Despite its apparent intensity, this starburst phase is only temporary. Astronomers estimate that within a few 100 million years, feedback from the central nucleus will likely suppress any further star formation, restoring the system to a much quieter state. The current burst may be just one single episode in a repeating cycle that spans the cluster's entire lifetime. Each cycle leaves behind a new population of stars, progressively building the galaxy's mass and enriching its environment. In this manner, Phoenix A evolves not through steady, gradual growth, but through alternating periods of calm and energetic renewal. The storm of star formation that is visible right now is simply one of those rare moments when cooling and gravity have temporarily prevailed over heat and equilibrium. In the silent blackness of space, the light from countless young stars radiates outward, crossing billions of years before it reaches our instruments. It tells a story of creation that is sustained by cosmic balance, where the birth of each individual star is both an effect of cooling and a precursor to renewed heating. Within the Phoenix cluster, this intricate dance between energy and matter continues without end, shaping one of the universe's most luminous and complex systems. Beneath the bright turmoil of star formation in Phoenix lies a deeper, more profound source of power, one that cannot be witnessed directly, but reveals its presence through the motions of gas and the glow of high-energy radiation. At the absolute center of the galaxy, buried deep within clouds of dust and complex layers of stellar light, resides a supermassive black hole whose influence extends across hundreds of thousands of light years. Its gravity governs the inner structure of the galaxy, drawing matter inward, even as its energy simultaneously drives material outward. Though the black hole itself emits no light, the process of accretion, the gradual infall of gas toward its event horizon, releases prodigious amounts of energy in the form of radiation, powerful winds, and focused jets. These manifestations form the basis of what astronomers call an active galactic nucleus, or AGN. In Phoenix A, this nucleus operates at an extraordinary intensity, generating enough energy to compete with the combined light of all the galaxy's stars. The clues to this hidden engine come from every single part of the spectrum. In X-ray observations, the central region appears brighter and harder than the surrounding gas, evidence of a compact source capable of heating nearby plasma to tens of millions of degrees. In radio maps, twin lobes of emission stretch outward from the nucleus, tracing jets that pierce directly through the surrounding medium. In optical data, faint emission lines reveal the presence of ionized gas moving at extremely high velocities, its excitation driven by ultraviolet and X-ray photons from the accretion disk. Together, these observations paint a detailed picture of a system powered by gravitational energy being converted into radiation, a process that transforms the slow infall of matter into a powerful feedback mechanism that shapes the entire cluster. The black hole's mass is estimated to be several billion times that of our Sun, placing it among the largest known in the nearby universe. Yet even such a colossal mass is dwarfed by the scale of its influence. The energy released by its accretion process is capable of heating or displacing gas across regions measured in hundreds of thousands of light-years. Despite this, the black hole remains concealed behind veils of gas and dust. Direct imaging reveals only the glow of material swirling around it at near relativistic speeds. The light from this region is highly variable, changing over timescales of years, sometimes brightening, sometimes dimming, as the flow of material shifts. Such variability strongly suggests that the accretion process is episodic rather than continuous, with periods of heightened activity separated by intervals of relative calm. Each active phase injects a massive amount of energy into the surrounding medium, inflating cavities and driving powerful shock waves that ripple through the cluster. These outbursts leave behind distinct signatures that persist long after the nucleus itself has quieted down. In the Phoenix cluster, those signatures are visible in the structure of the intracluster medium and in the arrangement of the cooling filaments. The relationship between the black hole and its environment is one of continuous exchange. As the gas in the cluster cools and flows inward, some fraction of it reaches the central regions, where it becomes gravitationally bound to the galaxy and is ultimately accreted by the black hole. This infalling material forms a rotating disk that heats up through friction as it spirals inward, producing radiation that spans from radio waves to gamma rays. Magnetic fields anchored in this disk channel some of the inflowing material into narrow jets that shoot outward along the poles at nearly the speed of light. These jets carry energy far from the nucleus, transferring momentum and heat into the surrounding plasma. The feedback from this process prevents the cluster's gas from cooling too rapidly, maintaining a delicate balance between inflow and outflow that defines the system's stability. In Phoenix A, this cycle operates with remarkable efficiency. Observations show that the rate of energy output from the AGN roughly matches the radiative losses of the cluster's core. This means that the black hole provides just enough heat to counteract the cooling, sustaining a near equilibrium state. If the output were even slightly higher, it could disrupt star formation entirely. If it were lower, cooling would accelerate, leading to a catastrophic collapse of gas toward the center. The precision of this balance implies that the feedback is self-regulating, controlled by the very processes it governs. As more gas flows inward, the black hole brightens, releasing energy that suppresses further inflow. When the gas supply diminishes, the activity fades, allowing cooling to resume. Over millions of years, this cycle repeats, its rhythm written in the cluster's X-ray light. The existence of such a mechanism explains how massive clusters like Phoenix can maintain stability over billions of years without exhausting their gas or collapsing into runaway starbursts. The AGN also influences the magnetic and chemical structure of its surroundings. The jets and winds generated by accretion mix the intracluster gas, distributing elements produced by stellar evolution throughout the entire cluster volume. They also amplify magnetic fields, creating a network of filaments that guide the motion of charged particles. These effects persist long after each outburst ends, shaping the medium through which new outflows will later propagate. Thus, the hidden engine not only regulates temperature, but continually reorganizes the physical environment, preparing the stage for subsequent cycles of cooling and heating. The evidence of this interplay is subtle but pervasive. High-resolution X-ray images show narrow edges and ripples near the core, shock fronts produced when jets and winds push into the surrounding gas. Radio data reveal synchrotron emission from relativistic electrons spiraling along magnetic lines. Optical observations capture filaments illuminated by the AGN's radiation, their shapes aligned with the directions of past outflows. Each data set contributes to the same conclusion. The center of Phoenix A is not static, but is alive with activity, driven by an unseen gravitational engine. The amount of energy involved defies intuition. A single outburst can release more energy than all the stars in the cluster will emit over their entire lifetimes. Yet, this energy is dispersed gently enough to preserve the cluster's overall structure. It heats the gas without destroying it, sustaining the delicate equilibrium that keeps the system luminous. Such control arises not from intent, but from the physics of feedback itself. Gravity draws matter inward. Radiation and jets push energy outward. Together, they establish a natural balance that requires no external tuning. The black hole's role is simultaneously destructive and creative. It halts excessive star formation, even as it ensures that new stars can continue to form in moderation. Without its influence, the Phoenix cluster would either cool into a dense ball of cold gas or dissipate into empty space. The AGN prevents both extremes, holding the system in a state of dynamic equilibrium. The presence of this hidden engine also connects Phoenix A to a broader class of galaxies where similar processes occur. From the giant ellipticals in the Perseus cluster to the central galaxies of Virgo and Coma, supermassive black holes serve as thermostats for their environments. Phoenix A represents one of the most extreme examples where the balance is pushed to its absolute limits and the consequences are written across the entire cluster. In its central glow, astronomers see not just a single galaxy, but the visible expression of a process that unites gravity, radiation, and matter across cosmic scales. The light from this system carries a message from deep time, that even in regions of apparent calm, unseen forces continue to shape the structure of the universe, their signatures imprinted in the faintest X-rays that reach us across billions of years. From the hidden engine at the core of Phoenix, immense streams of plasma erupt into the surrounding medium, traveling outward at nearly the speed of light. These are the jets, narrow beams of charged particles propelled by magnetic fields anchored in the accretion disk around the supermassive black hole. Though invisible to the human eye, they glow brightly in radio wavelengths, outlining a pair of oppositely directed lobes that extend far beyond the galaxy itself. Each jet carries a fraction of the black hole's accretion energy, concentrated into channels so focused that they remain collimated for hundreds of thousands of light years. As these jets emerge, they drill through the hot gas of the intracluster medium, displacing material and leaving behind cavities filled with relativistic particles. The energy required to carve such structures is immense, equivalent to the total output of trillions of stars. Yet, the process occurs gradually over millions of years, producing effects that are vast in scale, but gentle enough not to destroy the surrounding equilibrium. The paths of the jets are determined by the configuration of magnetic fields and the rotation of the black hole itself. Close to the event horizon, magnetic lines twist and tighten, channeling plasma into opposing directions along the spin axis. Once launched, the jets interact with the surrounding gas, generating bow shocks and turbulence. Some of the material slows and disperses, forming the lobes observed in radio light, while other portions continue outward, carrying energy deep into the cluster. This energy is deposited as heat through the dissipation of shock waves and the mixing of relativistic particles with the ambient plasma. The result is a slow, steady transfer of energy that offsets the radiative cooling of the cluster core. In Phoenix, the signatures of these jets are unmistakable. X-ray maps reveal cavities, regions of reduced brightness on either side of the central galaxy. These cavities correspond precisely to the radio lobes, showing that they are filled not with dense gas, but with magnetized plasma. Their edges are defined by compressed shells of hotter gas, evidence of shock heating as the jets push outward. The geometry of the cavities indicates that the outburst responsible for them was both symmetrical and powerful, releasing an amount of energy that ranks among the largest known from any black hole. Despite this, the surrounding gas remains largely intact, redistributed but not expelled. This gentle efficiency exemplifies the balance of feedback in galaxy clusters, where energy is injected not through violent explosions, but through persistent, regulated flows. The cavities act as buoyant bubbles that rise up through the integral cluster medium, carrying energy away from the core. As they ascend, they expand and eventually dissolve, mixing their contents with the surrounding gas. This process stirs the medium, generating turbulence that helps distribute heat evenly throughout the region. In doing so, the cavities serve as conduits for feedback, translating the concentrated power of the black hole into the diffuse warmth that prevents catastrophic cooling. The visible effect is subtle, a cluster that maintains its brightness and temperature profile without undergoing collapse or excessive heating. The physics governing the jet's stability is complex. Magnetic confinement prevents the streams from dispersing, while relativistic speeds minimize interaction with the ambient gas. However, as the jets propagate outward, they gradually lose coherence, spreading their energy over broader regions. The rate of this expansion determines how effectively they heat the cluster. In Phoenix A, the observed cavities suggest that the jets maintain stability over enormous distances before diffusing. Their longevity implies a consistent power output from the black hole, maintained over millions of years. Even a brief disruption could alter the symmetry or shape of the cavities, but the structures remain remarkably aligned, indicating that the central engine has remained stable over long periods. The interplay between jets and gas defines much of the cluster's appearance. Where the jets encounter denser regions of plasma, they slow and deposit more energy locally, creating bright rims of X-ray emission. Where the gas is more tenuous, the jets extend farther, sculpting elongated cavities that stretch into the cluster's outer halo. The distribution of these features provides clues to the history of the outburst. By measuring their size and estimating the pressure of the surrounding gas, astronomers can infer the total energy released and the timescale of the event. In the case of Phoenix A, the inferred energy rivals that of the most powerful known outbursts, though still below the record set by the Ophiuchus cluster. The comparison highlights the precision required to measure such phenomena, where differences in assumptions about cavity size, age, or ambient pressure can shift the calculated power by orders of magnitude. Beyond their mechanical effects, the jets also illuminate the cluster through radiation. The synchrotron emission produced by relativistic electrons spiraling along magnetic fields generates radio waves that trace the jet structure in exquisite detail. This emission fades gradually with distance from the core as the particles lose energy. In some regions, reacceleration occurs where the jets interact with turbulence or shock fronts, reviving the radio glow. These observations reveal a continuous dialogue between the black hole and the cluster medium, a conversation carried out through energy rather than sound. The balance between injection and dissipation defines the thermal state of the intracluster gas. Without these jets, the gas would cool unchecked, forming stars at rates far higher than observed. With them, the cooling is moderated, maintaining the cluster in a state of dynamic equilibrium. In addition to their thermal role, the jets contribute to the chemical and magnetic evolution of the cluster. They entrain and uplift metal-rich gas from the galaxy's core, redistributing it through the integral cluster medium. This mixing ensures that elements produced by previous generations of stars become part of the cluster's broader environment. The jets also strengthen and stretch magnetic fields, creating filamentary structures that help confine the cooling gas and guide its subsequent motion. These interactions illustrate how a process confined to the black hole's immediate vicinity can shape phenomena on scales measured in millions of light-years. Over time, repeated outbursts build a layered structure within the cluster. Cavities from earlier events overlapping those of newer ones, ripples of heat diffusing through the plasma, and filaments of cooler gas descending toward the center. Each layer records a phase in the feedback cycle, collectively preserving the history of the cluster's evolution. In Phoenix A, the most recent outburst appears relatively young, with cavities still sharply defined and shock fronts visible. This suggests that the central engine remains active, continuing to inject energy into the surrounding medium. Yet even as this occurs, the gas farther from the core continues to cool and flow inward, preparing the fuel for future episodes. The cycle thus perpetuates itself, alternating between creation and restraint, between the outward push of jets and the inward pull of gravity. From a distance, the process is invisible, hidden within the cluster's diffuse glow. But its consequences shape every aspect of the system. Through these jets, the black hole regulates its environment, maintaining a balance that allows the cluster to shine steadily across billions of years. The Phoenix cluster, though seemingly tranquil, is in truth a landscape sculpted by invisible forces, an equilibrium sustained by the ceaseless breath of energy flowing from its heart. The most striking evidence of the black hole's power within Phoenix A lies not in bursts of light, but in the voids it leaves behind. Surrounding the galaxy's core are immense cavities, dark, low-density regions etched into the hot plasma of the integral cluster medium. These hollows, carved by the force of jets streaming from the central black hole, act as long-lived monuments to the energy that was once released. Each cavity represents an outburst that inflated pockets of gas until they detached and rose slowly through the surrounding medium. Over time, these bubbles drift outward, their interiors filled with magnetized plasma and relativistic particles, invisible in optical light, but glowing faintly in radio frequencies. They record the memory of past eruptions, each one a measure of the system's ongoing attempt to balance cooling and heating. Astronomers read these structures much as geologists read layers of rock. By measuring their size, position, and pressure, they infer the history of events that shaped them. The physics of cavity formation begins at the heart of the galaxy, where jets driven by magnetic fields deposit energy into the dense core of the integral cluster gas. The pressure from this energy inflates lobes that push aside the surrounding plasma. As the cavities grow, they become buoyant and start to rise through the cluster, carrying their energy outward. The surrounding gas responds by forming rims of compressed material that glow brightly in X-rays, while the interiors appear as shadows in the X-ray maps. These contrasting regions allow scientists to calculate how much work the jets have done on the surrounding medium. In Phoenix A, the estimated energy required to form the cavities is extraordinary, on the order of 10 to the power of 60 ergs, enough to power an entire galaxy for hundreds of millions of years. Yet the process unfolds slowly and silently, more like the inflation of weather systems in an atmosphere than an explosion. The gas displaced by the rising cavities is not expelled, but redistributed, ensuring that the cluster structure remains largely intact. Each cavity rises until it reaches a point where its density matches that of the surrounding medium, at which point it begins to dissipate. During this ascent, it transfers heat and momentum to the surrounding plasma, gently stirring the gas and spreading energy over vast distances. The motion also generates turbulence, mixing the cluster's contents and delaying further cooling. Over billions of years, countless such events have likely occurred, each one leaving a faint imprint in the distribution of temperature and density within the cluster. The cavities visible today are simply the most recent examples, remnants of the latest episode in a cycle of activity that has persisted since the cluster's formation. The geometry of the cavities in Phoenix A provides a detailed record of the black hole's recent history. Two large, nearly symmetrical voids flank the central galaxy, aligned with the axis of the radio jets. Surrounding them are smaller, fainter depressions, possible relics of older outbursts, now partly filled in by gas. The symmetry suggests a stable orientation of the black hole's spin over many cycles, while the variety in size and brightness indicates differences in power or duration between events. The largest cavities extend for hundreds of thousands of light-years, their boundaries defined by shock fronts, where the gas has been gently compressed and heated. These fronts propagate through the cluster at supersonic speeds, leaving behind ripples that can be traced in high-resolution X-ray images. By analyzing these features, scientists can estimate the time elapsed since the outburst and the total energy released. In the case of Phoenix A, the cavities appear to be only a few tens of millions of years old, marking a recent phase of intense activity. The energy inferred from their size and surrounding pressure places the event among the most powerful ever measured in a galaxy cluster, though later observations suggest that the Ophiuchus cluster may hold the current record. This distinction, however, does not diminish the significance of Phoenix A, which remains one of the clearest examples of feedback operating on cosmic scales. The cavities serve as the visible interface between the black hole's output and the cluster's response. They illustrate how mechanical energy, injected through narrow jets, can become distributed throughout a massive environment without catastrophic disruption. The cavity's persistence also reveals the longevity of the feedback process. Unlike radiation, which dissipates quickly, the mechanical imprint of an outburst endures for hundreds of millions of years. Long after the central engine quiets, the buoyant bubbles continue to rise, their energy gradually absorbed into the cluster's thermal reservoir. As they rise, they entrain colder gas from the core, lifting it into the hotter regions of the cluster, where it can mix and reheat. This redistribution of material prevents the continuous buildup of cold gas at the center and moderates the rate of star formation. In this way, the cavities contribute not only to heating, but to the large-scale circulation that sustains equilibrium. Observations across multiple wavelengths reinforce this picture. In radio light, the cavities appear filled with synchrotron emission from relativistic electrons. In X-rays, they manifest as dim patches surrounded by brighter rims of compressed gas. At lower energies, weak shocks ripple outward, evidence of the moment when the cavities were first inflated. These combined signatures allow researchers to map the three-dimensional structure of the cluster's inner regions. By modeling how the cavities evolve over time, they can reconstruct the history of feedback and cooling. The results show a rhythm of activity, a repeating pattern of energy release, expansion, buoyant rise, and dissipation that maintains the thermal balance of the cluster. The process is remarkably efficient. Only a small fraction of the black hole's available energy is required to offset the entire cooling flow. The rest remains stored in the black hole's rotation or in magnetic fields near the event horizon, waiting for the next episode of accretion to release it. Over cosmic timescales, this balance ensures that the cluster neither freezes into stillness nor bursts into uncontrolled star formation. The cavities also offer insight into the physical conditions of the intracluster medium. By measuring the pressure at their edges and comparing it to the internal energy of the plasma they contain, scientists can estimate the composition and state of the relativistic gas. These studies suggest that magnetic fields play a crucial role in stabilizing the cavities, preventing them from collapsing under external pressure. The fields also confine the relativistic particles, allowing the bubbles to persist long after the jets that created them have faded. This magnetic scaffolding links the small-scale physics of plasma to the large-scale structure of the cluster, demonstrating how microscopic forces influence cosmic architecture. Over time, older cavities drift outward and fade, blending into the background as new ones take their place closer to the core. This layered arrangement forms a vertical timeline of activity, each level corresponding to a different epoch in the black hole's life. In Phoenix A, this stratification is particularly evident, with multiple generations of cavities marking successive outbursts. The pattern conveys both continuity and change. Continuity in the persistent feedback cycle, change in the varying intensity and reach of each episode. When viewed as a whole, the cluster becomes not a static object, but a dynamic record of energy flow, a cosmic palimpsest, where each new layer writes over the last without fully erasing it. Across these enormous empty spaces, the undetected mechanism at the cluster's core imprints its signature upon the cosmos. Its influence stretches substantially past the illumination it generates. Past the immense cavities that envelop Phoenix, subtle yet unmistakable undulations signify the cluster's most striking proof of energy in movement. These are the shock fronts, which are narrow barriers where the pressure, temperature, and density of the intracluster gas abruptly shift, thereby exposing the transit of waves propelled by previous energetic eruptions from the central black hole. When viewed in visible light, the cluster seems tranquil and undisturbed, its galaxies drifting without a sound through an expanse of dimly luminescent plasma. However, X-ray observations reveal an alternative truth: circular patterns and boundaries expanding outward from the center. These features are subtle yet clearly defined, resembling static reverberations from a faraway eruption. Every individual shock front maintains a history of energetic output from a previous time. Its specific form is sculpted by the medium around it, and its duration lasts for tens of millions of years. To our natural understanding, these formations may bring to mind the ripples generated by a pebble tossed into a placid pond. Although the magnitudes involved are impossible to fully conceive, in this environment each wave stretches across hundreds of thousands of light years and moves at velocities of thousands of kilometers per second through gas elevated to tens of millions of degrees. Nonetheless, the fundamental physical principles are fundamentally unchanged. When the black hole experiences an eruption of activity, powerful jets and winds infuse power into the dense core areas, creating an external force that compresses the gas in the vicinity. The subsequent shockwave propagates through the intracluster medium, transforming motion energy into thermal energy during its journey. When it finally becomes detectable by our equipment, the wave has decelerated and lost thermal energy, resulting in a minor yet quantifiable rise in temperature and density. These additions, while minor, are essential for preserving the cluster's heat equilibrium. Lacking them, the gas would lose heat much faster than it currently does, ultimately imploding into a concentrated mass of cold matter. Within Phoenix A, The detected shocks suggest that the black hole's feedback mechanism functions on durations of tens of millions of years, releasing energetic bursts adequate for reheating the cooling gas at periodic occurrences. The magnitude of these shocks is mild when contrasted with those from supernovae or other stellar detonations. They are categorized as weak shocks, their Mach numbers just slightly exceeding 1, which signifies they move only marginally quicker than the localized speed of sound within the hot plasma. Nevertheless, their collective impact across such enormous spaces is deeply significant. Every shock transports the equivalent of trillions of solar luminosities in the form of mechanical power, which is dispersed slowly throughout the medium. The exactness by which this energy counterbalances the loss of heat through radiation continues to be one of the most remarkable accomplishments of cosmic self-regulation. The specific geometry of the shock fronts offers insights into the historical activity at the cluster's center. In Phoenix, X-ray maps reveal a minimum of 2 separate rings of compressed gas located at varying distances from the core, indicating numerous energetic events divided by millions of years. The internal ring aligns with a recent occurrence that is still observable via its connected voids, whereas the external ring signifies a more ancient outburst, the consequences of which have mostly blended into the surroundings. The symmetrical nature of these features suggests that the black hole's axis of activity has stayed constant over extended durations, while their respective distances show the way power travels through the intracluster medium. By quantifying the sudden thermal increase across each front, astronomers can determine the speed of the shock and, from that data, approximate the complete energy implicated. In Phoenix A, these calculations produce figures that align with the immense power deduced from the voids, verifying that the identical event both expanded the bubbles and initiated the shockwave. This correlation reinforces the comprehension that jet cavities and shockwaves are linked components of a unified feedback mechanism. The movement of these shocks alters the cluster in minor, yet permanent fashions. As the wavefront travels externally, it squeezes the gas in its path, raising its density and temporarily boosting its X-ray luminosity. Following the front, the gas spreads out and chills marginally, establishing areas of reduced pressure that might subsequently direct the movement of ascending cavities. The overall result is a reallocation of thermal energy and momentum, which reestablishes balance without upsetting the cluster's complete framework. Over extended periods, recurring shockwaves create a pattern of subtle layering, arranging the gas according to temperature and density. This arrangement permits the cluster to maintain stability even when facing constant perturbation. The energy transported by the shocks also functions to stop disastrous cooling by reheating the gas in the central areas and propelling turbulence further outward. The waves reduce the speed at which matter gathers near the center. This process guarantees that the cooling flow stays manageable, supporting the star creation in Phoenix A without permitting it to speed up without restraint. In this manner, the shock fronts function as moderators within the larger cycle of feedback. They represent the external manifestation of the black hole's influence, distributing power from the tiniest levels of matter, gathering to the broader levels of the cluster's surroundings. Observations of comparable structures reveal that these waves are able to endure for hundreds of millions of years prior to disappearing into the surroundings. As they proceed, they deposit a gradual thermal slope that documents their journey. In Phoenix A, this thermal slope is exceptionally clear, verifying that the cluster's core has been heated again and again. The external areas stay hotter while the internal areas lose heat faster, preserving the circumstances required for new star creation. The interaction of heating and cooling, evident through these gradients, establishes the fragile balance that permits the cluster to persist. The discovery of shock fronts in Phoenix A likewise emphasizes the capability of contemporary observatories. Instruments such as the Chandra X-ray Observatory are able to resolve variations in luminosity of just a few percent across expanses covering hundreds of thousands of light-years. These minor variations, previously undetectable, now expose the intricate framework of feedback mechanisms in magnificent clarity. Utilizing such data, astronomers can rebuild the cluster's heat history, linking every observable undulation to an event of core activity. The developing image is that of a periodic power discharge, with every single pulse offsetting the depletion of heat from the gas. The black hole, though quiet and unseen, upholds this cadence using only its gravity, transforming the potential energy of material falling inward into the mechanical force that supports the cluster. Past their direct heat impacts, the shocks might also contribute to forming the magnetic and chemical arrangements within the cluster. As the waves journey outward, they strengthen magnetic fields and distribute heavy elements generated by the life cycle of stars. This distribution stops metals from sinking toward the center and guarantees a more consistent composition across the entire cluster. It also impacts the way future jets and outflows travel, as the magnetic structure of the medium shapes the direction and stability of later activity. Consequently, every shock not only documents history, but also readies the surroundings for what is to come. Over billions of years, the buildup of these consequences alters the cluster into a precisely calibrated system where heating and cooling stay balanced within tight constraints. The Phoenix cluster showcases this equilibrium at its most intense, merging energetic star creation with continuous feedback in one unified framework. Its shock fronts, cavities, and filaments jointly show the universal nature of the feedback cycle. Power discharged from an area only light hours in diameter can preserve stability within a framework covering millions of light-years. The waves expanding from Phoenix A's core are symbols of this link, their dim arches remaining visible across immense distances, signifying the pulse of a galaxy that exhales power into the enormous space surrounding it. At the center of the Phoenix cluster, every single process develops around a delicate balance: the cooling of gas that descends to the core, and the heating propelled by the black hole that propels power externally. This balance dictates if the cluster stays bright and stable or implodes into a dense starburst center. In the majority of clusters, feedback from the central black hole maintains the cooling flow in check. But in Phoenix A, the dual forces function with exceptional power, creating a system continuously at the brink of imbalance. The gas loses heat more rapidly than in nearly any other identified cluster. Nonetheless, the eruptions from the nucleus infuse sufficient warmth to stop an uncontrolled implosion. The outcome is a precisely balanced interplay where neither mechanism overwhelms the other for long. It is this ceaseless switching that supports both the continuous creation of stars and the bright luminescence of the intracluster medium. To comprehend how this balance is upheld, astronomers follow the movement of energy from one area to the next. As gas emits X-ray radiation, it sheds heat and starts to cool. Gravity draws it internally, where concentrations are greater and cooling speeds up. Concurrently, the central black hole reacts to the influx by gathering additional material, discharging power in the form of jets and radiation. These outflows expand voids, propel shock fronts, and agitate the surrounding plasma, restoring the warmth depleted through radiation. Over millions of years, this feedback establishes a cycle that self-moderates. When cooling grows stronger, additional material gets to the black hole, boosting its output. When heating grows too powerful, the gas spreads out, cooling decelerates, and the gathering rate declines. The system sways softly between these conditions, with every phase enduring for tens of millions of years. The Phoenix cluster provides one of the most vivid illustrations of this cosmic self-moderation. Observations demonstrate that the rate of cooling deduced from the cluster's X-ray emissions is nearly identical to the projected power discharge of the central active galactic nucleus. This close similarity signifies that the feedback loop functions with exceptional effectiveness. The power discharged by the black hole is adequate to counteract the heat depletion of the cluster core, but it is insufficient to completely halt the cooling. This type of equilibrium is uncommon. In numerous other systems, one process dominates the other. The Phoenix cluster's singularity is found in how near it gets to this boundary without ever moving past it. The interaction of heating and cooling is observable in the physical arrangement of the cluster. The core areas show cooler gas and ongoing star creation, whereas the external areas stay warm and spread out. This thermal slope mirrors the extent of the black hole's influence. The power infused at the center travels externally through cavities and shocks, slowly dispersing into the medium. As the power disseminates, it upholds the thermal structure needed to stop additional gathering. Concurrently, a portion of the gas that avoids the reheating successfully cools and gathers, fueling the star creation inside Phoenix A. The equilibrium among these results is upheld by the timing of the feedback. Eruptions of energy from the nucleus happen often enough to halt too much cooling, yet periodically enough to permit some of it to continue. This switching provides the cluster its signature cadence, one that can be deduced from the distance between voids and the age of the star-creating areas. At its center, this equilibrium is not stationary but active, controlled by a constant interchange. Power travels externally while material moves internally, and every mechanism relies on the other. The heating stops the cooling flow from becoming disastrous, while the cooling guarantees a reliable source of fuel to support the black hole. Neither one could function without the other. This mutual reliance contains the stability of the entire system. The process is similar to the balance of a biological entity, where power consumption and output have to equalize for survival. Although in this case, the durations are measured not in seconds or years, but in millions of years. The feedback loop functions through multiple physical pathways. Kinetic power from jets warms the gas immediately by way of shocks and turbulence. Ascending voids transfer power by exerting force on the surrounding medium as they grow and rise. Radiation from the accretion disk also adds, albeit less effectively, by charging and heating the gas in the vicinity. Every mechanism functions on varied levels, guaranteeing that heating is spread evenly rather than focused in one area. The outcome is a type of heat control that keeps the cluster near a stable condition. Minor variations happen when one process briefly overtakes the other, resulting in small cycles of activity that recur across cosmic ages. The proof of these cycles is imprinted on the framework of the gas and stars. The newest groups of stars in Phoenix A align with the most recent times of increased cooling, while the existence of voids and shocks signifies the following stage of reheating. In this manner, the galaxy's visual form mirrors its heat history. Luminous strands where cooling was strongest, uniform halos where heating was dominant, and intersecting areas where the two mechanisms intersected. The Phoenix cluster therefore functions as a testing ground for examining how cosmic systems uphold equilibrium when faced with immense power. One of the lasting puzzles relates to how feedback reaches such exactness. the black hole reacts to shifts in the accretion rate on durations much briefer than the cluster's cooling time. Nonetheless, the result stays constant over billions of years. This suggests that the feedback is controlled not by instantaneous response, but by extended period averages, where minor variations neutralize each other. The magnitude of the cluster evens out localized changes, creating the impression of equilibrium even while specific events differ in strength. Simulations of clusters indicate that this stability emerges organically from the connection between cooling gas and black hole accretion. The more gas that cools, the more powerful the eruption that comes after, and the more extended the subsequent dormant period. In Phoenix A, the cycle has probably recurred dozens of times since the cluster was created, every repetition modifying the equilibrium slightly, but never eliminating it. The power analysis of the cluster offers additional understanding. The complete power emitted in X-rays is quantified at approximately 10 to the power of 45 ergs per second, while the projected mechanical power of the black hole's jets is of a similar size. This parity demonstrates that the two mechanisms are secured in balance, each one offsetting the other. The effectiveness needed for such a match indicates a precisely adjusted feedback system functioning across numerous levels of scale, from the event horizon of the black hole to the million light-year expanse of the cluster. Even small changes would result in severe outcomes. Nonetheless, the system persists over time. This balance impacts the cluster's development. The constant interaction of heating and cooling stops the accumulation of cold gas while keeping sufficient fuel for star creation. It also safeguards the framework of the intracluster medium, stopping an implosion into a dense core. Lacking this control, the cluster center would have become a huge star-forming event ages ago, depleting its fuel supply and changing its makeup. In its place, Phoenix A stays bright, its feedback cycles recurring like the regular rhythm of a cosmic heartbeat. From a wider viewpoint, the balance seen here reflects mechanisms happening all across the universe. Every massive galaxy cluster contains a comparable battle between cooling and heating, although few show it as vividly as Phoenix. The identical principles that control this system form the development of galaxies on all levels. The Phoenix cluster's outstanding luminosity simply amplifies what occurs universally. Power discharged by black holes prevents the universe's biggest structures from becoming dormant. The equilibrium between cooling and heating, though undetectable by sight, supports the cosmic framework that generates light, structure, and time itself. The Phoenix cluster exists as a unique illustration of cosmic balance taken to its furthest limit. Nonetheless, its methods are not one of a kind. Across the known cosmos, clusters of galaxies show comparable arrangements of cooling flows, jet propulsion, and feedback cycles, everyone adhering to the identical basic concepts of power moderation. To comprehend Phoenix A completely, astronomers contrast it with other thoroughly examined systems, looking for variations that provide a measure of what makes this particular cluster so extraordinary. Among the most commonly examined comparisons is the Perseus cluster, whose central galaxy NGC 1275 displays comparable cavities, filaments, and mild shock waves. In that location, just as in Phoenix, jets from a supermassive black hole expand bubbles of high-speed plasma that ascend through the intracluster medium, warming it and stopping runaway cooling. However, Perseus functions at a milder level. Its star creation speed is slower, its gas is cooler and not as dense, and its feedback is less aggressive. The Phoenix cluster appears to signify the identical physical cycle, but under much stronger conditions, as if the variables of temperature, density, and power had all been elevated to their maximum values. The comparison permits scientists to validate ideas about feedback effectiveness, jet strength, and gas dynamics in different situations. In both of these systems, the proportion of cooling to heating stays precisely equalized, indicating a globally applicable process that functions regardless of size. Past Perseus, comparable mechanisms are seen in clusters such as Virgo, Hydra A, and Centaurus. Every one contains a huge central galaxy that has a dynamic core, which discharges power intermittently into the areas around it. The shape of their X-ray cavities and radio lobes shows that feedback is present in all massive clusters. What sets Phoenix apart is the strength of its cooling flow and the extraordinary speed of star creation in its central galaxy. While other clusters demonstrate minor rejuvenation, Phoenix A generates stars at hundreds of solar masses annually, competing with galaxies in the primordial cosmos. This irregularity questions theories that forecast feedback ought to completely stop such activity. It suggests that the system is being observed in a short period when cooling and heating are almost, but not completely, balanced. Viewing it at this point provides a unique look into the intermediate phases that form galaxy development. The commonalities among clusters reach into their fundamental physics. In all situations, the power discharged by a black hole's accretion mechanism must be equal, on average, to the power depleted by the gas through radiation. This requirement guarantees equilibrium, but the method of attainment can differ. Some systems depend more upon kinetic feedback by way of jets, others on thermal radiation or cosmic ray diffusion. The Phoenix cluster shows that these pathways can function concurrently. Jets infuse mechanical power that creates voids and propels shockwaves, while radiation from the accretion disk warms the nearby environment. Jointly, they uphold the thermal and pressure balance of the intracluster medium. The comparison of clusters likewise shows the significance of the environment. Clusters with concentrated centers and rapid central cooling speeds usually generate more powerful feedback, while those with lesser concentrations stay comparatively dormant. The Phoenix cluster is located at the far end of this spectrum, where cooling is most rapid and feedback is most powerful. This location establishes it as a standard for comprehending how feedback correlates with cluster mass and gas density. The insights gained from Phoenix improve theories of galaxy formation across all of cosmic history. The mechanisms seen here are larger iterations of those happening in less massive galaxies. In both situations, black holes control their surroundings through the identical cycle of accretion, outflow, and reheating. On galactic levels, this feedback dictates the speed of star creation and the expansion of the group of stars. On cluster levels, it manages the heat framework of the intracluster medium and the lifespan of the system in its entirety. Therefore, by examining Phoenix A, astronomers get understanding of the development of galaxies universally. The feedback systems that maintain the cluster's stability are believed to have functioned since the very first eras of galaxy formation, forming the arrangement of matter throughout the cosmos. Comparisons with farther clusters, seen as they existed billions of years ago, uphold this consistency. Even in the early cosmos, when black holes were more dynamic and galaxies were more filled with gas, the identical interaction of cooling and heating is observable. Phoenix A might, as a result, signify a primordial mechanism persisting into our current time, maintained in its intense conditions. One of the most fascinating similarities emerges in the analysis of metallicity, which is the quantity of heavy elements found within clusters. In every situation, feedback mechanisms reallocate metals from the central galaxy into the nearby environment. The jets and cavities function as channels, moving enhanced matter externally. This distribution stops metals from sinking toward the center and guarantees a more consistent makeup across the cluster. It also impacts the way future jets and outflows travel, as the magnetic structure of the medium shapes the direction and stability of later activity. In Phoenix A, the heavy element distribution reflects that of Perseus and Virgo, showing that regardless of its intensity, the feedback mechanism maintains the identical overall framework. This commonality strengthens the concept that feedback is a global moderator, functioning uniformly across hugely varied environments. Another shared characteristic among clusters is the endurance of magnetic fields. Although faint, these fields form the movement of gas and direct the transfer of energy. In systems such as Hydra, strong radio emissions expose organized magnetic frameworks inside the cavities. In Phoenix, a comparable arrangement is presumed, although the larger distance makes detection more challenging. Theoretical models indicate that these fields are strengthened by the identical jets that expand the voids, connecting magnetism to feedback and stability. Across all observed clusters, magnetic containment permits bubbles to endure for hundreds of millions of years, upholding the circumstances required for slow power reallocation. When the Phoenix cluster is contrasted with systems having black holes that are not as massive, an additional pattern becomes clear. The scale of feedback links tightly with black hole mass and the gathering speed. In clusters where the central black hole is not as massive, the feedback cycle moves more gradually and with lesser magnitudes. Phoenix A, possessing its black hole of several billion solar masses, functions at the highest end of this relationship, generating eruptions capable of warming the cluster on durations briefer than the cooling time. This correlation across systems indicates that feedback effectiveness is fractal-like, controlled by the identical physics independent of scale. It suggests that black holes of all masses engage with their environments in a similar fashion, modifying their power to uphold balance. The Phoenix cluster therefore functions as both a testing ground and a point of comparison. By examining it, astronomers can check if theories of feedback developed from other clusters stay accurate at the maximum power levels. Initial findings show that they do, backing the concept of universality and cosmic feedback. However, the intense conditions found in Phoenix show subtleties missing in other places. The rapid cooling, the powerful outflows, and the simultaneous presence of intense star creation with massive heating indicate that the feedback loop can near imbalance without collapsing. This fragile threshold, seen here in equilibrium, might signify the intermediate phase that all clusters move through at some point in their development. The Phoenix cluster, therefore, is not an anomaly, but rather a photograph of a global mechanism functioning at maximum capacity. When contrasted with its contemporaries across the cosmos, it demonstrates that even within the most energetic systems, nature moves toward equilibrium. The identical laws that control a tiny galactic nucleus in the nearby cosmos also manage the most massive structures identified, connecting the destiny of galaxies, black holes, and clusters in a unified spectrum. In this common design resides the crucial insight to comprehending how the universe upholds its framework across billions of years, utilizing cycles of decay and rebirth that keep even the biggest systems active and bright. The detection of the enormous voids inside Phoenix A at one time prompted many astronomers to announce it as the location of the strongest black hole-propelled outburst ever documented. Initial studies of X-ray and radio data indicated that the power needed to create those empty spaces exceeded everything formerly quantified, eclipsing even the well-known events in Perseus and Hydra A. The approximation positioned the complete outburst energy in the vicinity of several times 10 to the power of 60 ergs, comparable to hundreds of millions of supernovae exploding simultaneously. For many years, this number served as a standard, a clear illustration of how one single black hole could form a framework stretching across millions of light years. Nevertheless, as quantifications refined and fresh data appeared, a subtle discussion commenced. Other clusters, most prominently Ophiuchus, seemed to display even bigger voids and wider shock waves, suggesting eruptions of similar or larger magnitude. The record itself, it appeared, relied upon how an individual characterized and quantified such power. The Phoenix cluster consequently became not just a testing ground for comprehending feedback, but also a test case in how science sharpens its comprehension through contrast and adjustment. Quantifying the power of a cosmic eruption is not at all simple. Astronomers are unable to view the event firsthand. They must deduce its power from the marks it deposits on the gas in the vicinity. The volume of the voids, the temperature of the shock-warmed areas, and the duration over which bubbles ascend all factor into the calculation. Every one of these variables contains ambiguities. A minor shift in presumed pressure or density can change the outcome by many orders of magnitude. Additionally, the categorization of an eruption as the strongest relies on the standard one employs: complete power discharged, maximum power discharge, or impact on the surrounding medium. For Phoenix, the initial models employed a specific mix of assumptions that stressed complete power, whereas subsequent studies utilized more cautious parameters. The outcome was not a conflict, but rather an improvement, a sharper perspective of the physical situation. The seeming reduction of Phoenix's record did not diminish its importance. Instead, it clarified the comprehension of the interaction of data, models, and interpretation. The Ophiuchus cluster, whose eruption was publicized subsequently, showed voids so massive that they made even those in Phoenix look small by comparison. X-ray observations revealed a single bubble more than 1 million light-years in diameter, suggesting a power discharge approximately 5 times larger than the Phoenix approximation. The comparison, nonetheless, is complex. The Ophiuchus eruption seems to have happened further in the past and in a more concentrated medium, signifying that a large portion of its power was transformed into widespread movement instead of thermal energy. Phoenix, in contrast, shows a more focused engagement between the jets and the intracluster medium, where a large portion of the power was dedicated to moderating cooling and supporting star creation. Consequently, while Ophiuchus might possess the record for complete energy, Phoenix continues to be a template for effectiveness, where feedback immediately forms the continuous existence of the cluster. This difference shows the complexity of astrophysical occurrences that defy easy categorization. The discussion about these records reveals how observations change with new tools. Instruments like the Chandra X-ray Observatory and the Atacama Large Millimeter Array offer unmatched clarity, but they likewise reveal the boundaries of interpretation. X-rays reveal temperature and density. Radio waves follow high-speed electrons, while optical and infrared data chart star creation and cold gas. Every collection of data provides an incomplete perspective, and only by combining them can astronomers rebuild the complete history of an eruption. In the Isai-Thor situation of Phoenix A, merging these data has demonstrated that its feedback functions via several pathways: mechanical, thermal, and radiative, each one adding in varied ways to the cluster's equilibrium. The question of which cluster generated the biggest detonation is consequently less significant than comprehending how such power impacts its surroundings. Detailed understanding supersedes rivalry. The true wonder is found not in setting records, but in witnessing the consistency of physical laws across hugely varied systems. The debate likewise highlights the significance of perspective in cosmic observation. Because light requires billions of years to journey from faraway clusters, every system provides a photograph of a separate era in cosmic history. The Phoenix cluster, whose light has journeyed for about 6 billion years to get to Earth, displays feedback functioning at a moment when the universe was approximately one-half its present age. The Ophiuchus cluster, nearer and thus more recent in the timeline, signifies a subsequent phase in cluster evolution. Comparing the two permits astronomers to investigate the ways feedback processes may alter across cosmic ages. Whether black holes became more efficient, whether gas cooling slowed, or whether environmental differences dominate. In this respect, the debate broadens beyond records to a more profound inquiry about the evolution of structure in the universe. The method of quantifying cavity power demonstrates both the complexity and the ambiguity of modern astrophysics. To calculate the complete energy of an eruption, scientists approximate the pressure of the surrounding gas from its X-ray brightness, multiply it by the cavity's volume, and then consider the upward drift duration to determine the power discharge. This approach, though refined, presumes that cavities are symmetric and that their interiors contain high-speed plasma in pressure balance with the ambient medium. In actuality, these assumptions seldom are completely accurate. Cavities can be asymmetrical, filled with magnetic fields or cosmic rays of varying density. Some may overlap or blend with older structures, making age calculations difficult. The Phoenix cluster demonstrates these difficulties. Its cavities overlap with areas of active star creation, suggesting that feedback and cooling happen concurrently. Such complexity resists easy categorization. The ongoing discussion about its outburst power thus highlights the necessity for care in comparing numbers derived from very different systems. Recent advancements in simulation have assisted in explaining these vagaries. Digital simulations now recreate the feedback cycle observed in Phoenix and Ophiuchus, showing how differences in environment and black hole accretion rate result in varied visible results. In simulations that match Phoenix, the jets distribute power more uniformly, inflating moderate cavities and driving continuous turbulence that mixes the intra-cluster medium. In those resembling Ophiuchus, the energy is released in less frequent but more powerful episodes, creating enormous voids but less ongoing heating. These variations underscore the flexibility of the feedback process, which can manifest as either steady breathing or rare eruptions, depending on the cluster's conditions. Within this framework, the idea of a record becomes irrelevant. What is important is how energy forms the framework and upholds equilibrium. The discussion surrounding Phoenix A also shows the scientific method at its finest. The openness to re-examine earlier conclusions, to improve theories with new data, and to view seeming conflicts as opportunities for deeper understanding all illustrate how understanding progresses. What previously appeared as the most powerful event became, through closer examination, part of a spectrum of activity shared by many clusters. This shift does not reduce Phoenix's importance. It raises it as a standard against which others are measured. Even as its record yields to Ophiuchus, its role as a model for stable feedback remains uncontested. The cluster continues to represent the fragile coordination of processes that keep cosmic systems active: cooling flows, heating episodes, star formation, and accretion, all connected through the invisible hand of gravity. In the end, the debate over which cluster possesses the distinction of greatest outburst reflects something central to the nature of science itself. Rankings are fleeting, but comprehension persists. Phoenix A's outburst, whether first or second in power, remains a foundation in our understanding of how black holes influence the universe. Its cavities, shocks, and starburst core demonstrate a fact repeated from one cluster to another: that the universe's largest explosions are not events of annihilation, but tools for equilibrium, maintaining stability amid energy. Through Phoenix A and its successors, the cosmos reveals that even its most violent events fulfill a calm, supportive role, ensuring that galaxies, clusters, and the space between them remain in motion, bright and active. At the gravitational core of Phoenix lies the real designer of the cluster's balance: a supermassive black hole whose mass is measured in billions of suns and whose influence reaches across the galaxy and into the surrounding plasma. Though invisible, it determines the motion of the system, forming the paths of stars and the flow of gas through its immense gravitational field. The black hole itself is smaller than the orbit of our solar system, yet the energy it releases through accretion regulates a structure millions of light-years wide. Its event horizon forms the boundary beyond which nothing, not even light, can escape. Around this region swirls an accretion disk of gas drawn inward by gravity, but prevented from immediate collapse by its own angular momentum. The material in the disk heats to extraordinary temperatures, radiating across the electromagnetic spectrum. Some fraction of this infalling matter never crosses the horizon. Instead, it is redirected by magnetic fields into narrow jets that carry energy outward. In Phoenix A, this process has been active for hundreds of millions of years, sustaining a continuous dialogue between the smallest and largest scales of the cluster. The black hole's mass is estimated to be several billion times that of the Sun, a value inferred from the luminosity of the surrounding gas and from empirical relations linking black hole mass to galaxy properties. Though uncertain by nature, this estimate places it among the most massive black holes known. Its gravitational reach extends far beyond the galaxy's nucleus, influencing the motion of stars within tens of thousands of light-years. Yet its most remarkable property is not its mass, but its efficiency. Through accretion, it converts gravitational potential energy into radiation and kinetic energy with efficiencies approaching 10%, far higher than any known stellar process. This conversion powers the jet cavities and shocks that define the Phoenix cluster structure. Without it, the cluster's gas would cool uncontested, collapsing into new stars until no free plasma remained. The energy released near the event horizon thus sustains the brightness of the cluster billions of light-years away. A connection that links the fate of an entire galaxy cluster to the behavior of matter orbiting a point of infinite density. The physics governing this engine remains one of the most studied topics in astrophysics. In the simplest description, gas falling into the black hole loses gravitational potential energy, which is transformed into heat and radiation. Magnetic fields anchored in the rotating disk extract angular momentum, allowing the gas to spiral inward. These same fields channel some of the energy into columnated outflows that escape along the rotational axis. The jets carry a mixture of plasma and magnetic flux, forming the large-scale structures observed in radio wavelengths. The balance between inflow and outflow determines how much mass the black hole gains over time. In Phoenix A, the evidence suggests that accretion proceeds at a moderate rate, neither a full quasar phase nor a dormant state. This intermediate activity level may explain why feedback remains continuous rather than episodic, maintaining equilibrium instead of alternating between violent bursts and silence. The radiation from the accretion disk interacts with the surrounding gas in complex ways. Near the nucleus, X-rays and ultraviolet photons ionize the inner regions, creating a halo of hot plasma. Farther out, radiation pressure influences the dynamics of cooler clouds, sometimes driving them away from the center, sometimes compressing them into denser forms that can later feed the black hole. Again, this interplay of radiation, gravity, and magnetic forces governs the rate at which the black hole consumes material and the pattern of energy it releases. Observations of Phoenix reveal that the nucleus flickers over time, brightening and fading in rhythm with changes in accretion. These variations occur on time scales of years to decades, short compared with the cluster's age, but long enough to influence the thermal state of the surrounding gas. Each increase in luminosity sends a pulse of energy through the environment, inflating cavities and generating shocks that propagate outward. Each decline allows cooling to resume, replenishing the fuel for the next cycle. The black hole thus acts as the heart of the system, its activity setting the tempo for the cluster's long-term evolution. The scale of its influence defies intuitive understanding. The mass enclosed within its event horizon would fit inside the orbit of Neptune. Yet its energy output shapes a volume millions of light-years across. This apparent paradox arises from the efficiency of gravitational conversion. Matter falling toward the black hole accelerates to relativistic speeds, and a small fraction of its rest mass energy is liberated before disappearance. Even a trickle of accretion, when sustained over millions of years, produces enough power to counter the cooling of the entire cluster. In this sense, the black hole operates as a thermostat, injecting energy when needed and resting when balance is restored. Its self-regulation emerges naturally as more gas cools and flows inward. The accretion rate increases, boosting energy output. When heating dominates inflow, diminishes, reducing the black hole's activity. The result is a cosmic feedback loop that maintains near equilibrium without external guidance. The black hole's presence also affects the structure of the central galaxy in more subtle ways. The gravitational potential near the core stabilizes stellar orbits, preventing the dense inner regions from fragmenting under self-gravity. The radiation from the nucleus influences chemical evolution by ionizing elements and driving outflows that mix enriched gas with the surrounding medium. Even the morphology of the galaxy, its smooth contours and diffuse light, reflects the steady influence of its central mass. Over billions of years, feedback from the black hole has sculpted Phoenix A into its current form, regulating not only its gas, but also its stars. The relationship between the black hole and its host galaxy exemplifies a pattern seen throughout the cosmos. Observations show that the mass of a galaxy's central black hole correlates closely with the mass of its stellar bulge, suggesting co-evolution. Phoenix A fits this relationship, though at the extreme end of both parameters. Its massive bulge and vast halo of stars testify to a long history of growth governed by feedback cycles. Each phase of intense accretion likely triggered corresponding bursts of star formation, followed by quiescent periods when feedback suppressed further growth. Over time, these alternating epochs brought the system to its present state, a mature galaxy sustained by the same process that once threatened to disrupt it. The study of Phoenix A's black hole also informs broader theories about the role of such objects in cosmic evolution. Across the universe, supermassive black holes act as regulators, preventing galaxies and clusters from overproducing stars. They shape the temperature and composition of the intergalactic medium, influence large-scale structure formation, and determine the distribution of matter in the cosmic web. The Phoenix cluster, with its extreme conditions, provides an ideal setting to test these ideas. By observing its nucleus, astronomers can connect small-scale physics to cosmological outcomes, linking the infall of gas across event horizons to the fate of galaxy clusters billions of light-years away. In this view, the black hole at Phoenix A's center is not merely an object, but a process, a continuous conversion of gravity into light, order, and balance. It demonstrates how even in the universe's most violent realms, stability arises from the interplay of opposing forces. The darkness at the cluster's core is thus both the origin and the guardian of its light. Around the black hole at the heart of Phoenix, matter flows inward in a slow spiral, drawn by gravity, yet resisted by angular momentum and magnetic pressure. This inward drift, known as accretion, is one of the universe's most efficient engines of energy conversion. Gas falling toward the event horizon releases gravitational potential energy as heat and radiation, forming the accretion disk, a flattened, rotating structure of plasma reaching temperatures of millions of degrees. The light from this disk cannot escape the surrounding layers of dust and gas directly, but its influence extends far beyond visibility. It drives winds, launches jets, and sets in motion the feedback that sustains the cluster's equilibrium. In the Phoenix cluster, this process operates on an immense scale, transforming microscopic motions of charged particles near the event horizon into macroscopic changes spanning millions of light-years. The energy output depends on the rate at which gases are created. If the inflow becomes too strong, radiation pressure builds until it pushes material away, temporarily throttling the process. If the inflow weakens, the disk cools, and the black hole dims, allowing gas to accumulate again. This self-regulating mechanism maintains an average balance over time. In Phoenix A, the cycle manifests as alternating periods of quiet accretion and intense activity, each lasting millions of years. During active phases, matter within the disk moves at relativistic speeds, colliding and compressing until magnetic fields twist into tight spirals. These fields extract rotational energy from the black hole, channeling it into jets that emerge along the poles. The jets carry energy outward through the galaxy, inflating cavities, generating shock waves, and stirring the intracluster medium. The entire sequence, accretion, radiation, jet formation, and feedback, constitutes a closed loop that connects the smallest and largest structures in the cluster. The physics of this interaction can be understood through the language of balance and flow. As the black hole feeds, it converts a small fraction of mass into energy with extraordinary efficiency. For every kilogram of material consumed, nearly a tenth of its rest mass becomes radiation or kinetic energy. That energy then diffuses through the cluster, heating gas and preventing further collapse. The process is remarkably stable because it is governed by feedback. An increase in accretion strengthens the outflow, which in turn reduces the inflow, restoring equilibrium. The cycle is comparable to the regulation of a flame by its own heat, maintaining a steady burn despite constant changes in supply. In the case of Phoenix A, this flame burns across millions of light-years, invisible yet essential. The evidence of these feedback motions appears in the structure of the surrounding gas. X-ray and radio maps reveal cavities where jets have displaced material, while optical observations show filaments of cool gas drawn inward along gravitational paths. These filaments occasionally intersect with the edges of cavities, suggesting that inflow and outflow occur simultaneously. The interaction between the two generates turbulence, which mixes hot and cold phases and promotes thermal stability. In this churning environment, energy is neither trapped nor lost, but recycled, passing through different states and locations before settling back into equilibrium. The cluster's ability to sustain this balance over billions of years demonstrates the resilience of the feedback process. The accretion disk itself is a site of extreme physics. At its inner edge, matter approaches the event horizon at velocities close to the speed of light. Friction and magnetic reconnection release enormous heat, producing X-rays that illuminate the surrounding region. Beyond this radius, cooler zones of the disk emit ultraviolet and optical light, though much of it is absorbed and reprocessed by dust. The result is a multi-layered system where each band of radiation originates at a specific distance from the black hole. Observations of similar systems suggest that such disks are turbulent, with magnetic fields constantly amplifying and breaking. This turbulence governs how angular momentum is transferred outward, allowing gas to fall inward. The process is not smooth but chaotic, punctuated by bursts of enhanced emission when magnetic loops reconnect and release stored energy. These fluctuations correspond to the flickering seen in Phoenix A's nucleus, the visible heartbeat of the accretion process itself. Feedback in motion extends beyond the core into the broader cluster environment. As jets move outward, they entrain gas and create pressure gradients that propagate as sound waves. These waves dissipate their energy, gradually warming the plasma without disrupting its structure. The same waves likely contribute to the faint ripples observed in X-ray brightness around the galaxy. Each ripple represents a minor adjustment in the cluster's energy balance, a correction to cooling that prevents runaway collapse. Over cosmic time, countless such waves have passed through the cluster, each one adding a small measure of heat and maintaining stability. This coupling of mechanical and thermal processes makes the feedback cycle robust, capable of enduring changes in accretion rate, jet direction, or magnetic configuration without losing overall coherence. The connection between accretion and feedback also determines how the black hole evolves. As it consumes matter, its mass grows, deepening its gravitational well and slightly altering its spin. The spin, in turn, affects the strength of the jets. A rapidly rotating black hole can power stronger outflows by tapping into its rotational energy. In Phoenix A, the alignment and persistence of the jets suggest a stable, rapidly spinning black hole that has maintained its orientation for hundreds of millions of years. This stability ensures that feedback remains directed and efficient, minimizing waste and maximizing influence on the cluster's core. Over time, the balance between growth and regulation may bring the black hole to a saturation point, where feedback prevents further significant accretion, locking the system into long-term equilibrium. The interplay of inflow and outflow defines not only the physics, but also the appearance of the cluster. The luminous starburst regions owe their existence to cooling gas that escape the reach of heating, while the cavities and shock fronts mark the boundaries where feedback has restored temperature. The result is a landscape of contrasts: cool filaments illuminated by young stars, hot bubbles shining in X-rays, and a nucleus radiating across all wavelengths. Each feature represents a stage in the ongoing exchange of matter and energy, a visual record of feedback in motion. To an observer, the cluster might appear tranquil, but beneath its calm exterior, countless processes unfold in concert, all coordinated by gravity and feedback. This orchestration ensures that no part of the system remains isolated. The energy released at the event horizon travels outward through the jets, interacts with the plasma, and returns indirectly as fuel for further accretion. The loop closes as gas cools and flows inward again, continuing the cycle. The Phoenix cluster exemplifies how nature sustains equilibrium through feedback, converting what would otherwise be destructive energy into a mechanism of preservation. Across billions of years, accretion and feedback have maintained this vast structure in near-perfect balance, showing that even the universe's most violent forces can produce enduring stability when bound by gravity's quiet order. Even after decades of observation, Phoenix A remains one of the most perplexing and illuminating systems in the cosmos, a structure where the boundaries between creation and destruction blur. Its vast cluster glows steadily, its gas both cooling and heated, its stars both ancient and newly born, and its central black hole both restrained and immensely powerful. Each observation deepens understanding while raising new questions. The balance of forces within this cluster appears exquisitely tuned. Yet the precise mechanism that maintains it is not fully understood. Why does the black hole's feedback so precisely counteract cooling? How does star formation continue amid such heat and turbulence? And what determines the rhythm of outbursts that punctuate the cluster's long life? These questions guide ongoing research, linking Phoenix A to the wider study of cosmic feedback, galaxy formation, and the evolution of large-scale structure. Modern observatories continue to probe this enigmatic system with increasing precision. The Chandra X-ray Observatory maps the distribution of hot gas, revealing cavities, ripples, and shocks that testify to the black hole's power. The Hubble Space Telescope traces the optical filaments of cool gas stretching across tens of thousands of light-years. The Atacama Large Millimeter Array detects molecular clouds that serve as the raw material for star formation. More recently, the James Webb Space Telescope has added infrared detail, exposing regions of dust and newborn stars invisible in earlier surveys. Together, these instruments show a system of staggering complexity: cold gas condensing in the shadow of hot plasma, young stars forming where feedback should prevent them, and energy rippling through a medium that never settles into stillness. The Phoenix cluster thus serves as a microcosm of the universe's contradictions, a place where opposing forces coexist and sustain each other. One of the enduring mysteries is the persistence of its starburst. In most clusters, feedback from the black hole eventually quenches star formation, reheating the gas and dispersing the cold reservoirs needed for new stars. In Phoenix A, however, star formation continues at a pace that defies expectation. The rates measured suggest hundreds of solar masses of new stars forming each year, a level typical of galaxies in the young universe rather than those in the present epoch. This activity implies that cooling remains effective even in the presence of strong feedback. Some researchers propose that the jets and outflows themselves may trigger star formation by compressing gas clouds along their paths. Others suggest that the geometry of the cavities allows certain regions to shield from heating, preserving conditions for collapse. Whatever the mechanism, the coexistence of heating and star formation in the same system challenges models of cluster evolution and hints that feedback may act not only as a suppressor, but also as a catalyst for renewal. The black hole's role in this process continues to draw scrutiny. Its mass, estimated in the billions of solar masses, places it among the most massive known. Yet its accretion rate appears modest compared to its potential. This disparity raises the question of how such a massive object regulates itself so precisely. The current understanding suggests that feedback from earlier epochs has limited the available fuel, allowing only intermittent feeding today. The resulting low-efficiency state produces mechanical energy through jets rather than luminous radiation. This mechanical mode of feedback dominates in massive clusters like Phoenix, where dense plasma confines the jets and transforms their energy into heat. Despite this apparent stability, the system's long-term evolution remains uncertain. The balance between cooling and heating could shift with time as the black hole's fuel supply changes or as mergers with other galaxies disturb the equilibrium. Indeed, galaxy clusters are not static. they evolve through collisions and accretion of smaller groups. Such events can compress gas, ignite new waves of star formation, and briefly alter the feedback cycle. The Phoenix Cluster's future may depend on such interactions, each capable of resetting the delicate relationship between its components. Observations suggest that the cluster has undergone past merges, as indicated by asymmetries in its X-ray brightness and the motion of its galaxies. These events may have delivered the fresh gas that now fuels the black hole and its surrounding starburst. If so, the current phase of activity could be temporary, a flare in a much longer history of quiescence and reawakening. Yet, even if transient, this phase offers valuable insight into the physics that governs the universe's largest systems. Every photon that reaches Earth from Phoenix A carries information about processes operating across scales, from the subatomic to the intergalactic. The gas temperatures reveal heating and cooling rates. The cavity structures encode energy transfer. The spectral lines trace motion, composition, and density. When combined, these data form a coherent picture of feedback at work. And yet, beyond the measurable quantities, a deeper puzzle remains: how such complexity produces simplicity. Despite its internal chaos, the cluster behaves predictably when viewed as a whole. Its global properties, temperature, luminosity, and structure, remain remarkably stable. This constancy suggests that feedback, though driven by chaotic microphysics, yields order on macroscopic scales. The Phoenix Cluster thus embodies the principle of self-organization that runs through the universe. From turbulence emerges equilibrium. From violence arises continuity. This understanding transforms how astronomers view black holes. Once considered purely destructive, they are now recognized as essential to the universe's regulation. Without their energy, clusters would cool uncontrollably. Galaxies would overproduce stars and exhaust their gas. With them, the universe maintains its diversity and longevity. Phoenix A demonstrates this truth in its most dramatic form, revealing that even the most powerful explosions serve the purpose of preservation. The cluster's light, traveling for 6 billion years, arrives as both record and reminder. A record of the forces that shaped it, and a reminder that balance in nature often arises from opposition. The study of Phoenix A continues not only because it is bright and beautiful, but because it represents a question without a final answer. Every new observation refines models, yet leaves something unexplained. Perhaps the ultimate enigma is not the mechanics of jets or the energy of cavities, but the persistence of harmony in a system so vast and dynamic. The Phoenix Cluster endures as proof that equilibrium is not the absence of motion, but the result of motion perfectly countered. Its black hole, its gas, and its stars together compose a single organism whose life is measured in cosmic time. For scientists, it remains a natural laboratory for testing the physics of gravity, magnetism, and thermodynamics on the grandest scales. For the universe itself, it is another expression of a principle older than galaxies. That energy once released never vanishes, but becomes the quiet scaffolding upon which structure stands. As research continues with ever more sensitive instruments, Phoenix A will likely yield further surprises, subtler ripples, hidden filaments, or faint echoes of earlier outbursts. Yet its mystery will endure, for its true significance lies not only in what it reveals, but in how it connects the smallest and largest realms of existence. The Phoenix Cluster remains luminous, vast, and in delicate balance. A living equilibrium in which cooling and heating, order and chaos, destruction and creation coexist, shaping the ongoing rhythm of the universe itself.